Hello everyone, welcome to week 9 live session of digital electronic circuits. So today we'll solve some questions that may help you in your assignment as well as in your exams. Am I audible clearly?
Yes, sir.
So please feel free to ask any questions in between. You can use your mic also, or if you want you can type in chat also. Okay, so let's start. So first question is, a ripple counter with positive edge trigger flip-flop is given below. If the present state of the counter is 000, then the next state will be. So let's try to solve this. So currently we have 0 0 0. So if you remember t flip-flop from the last lectures, when t equals to 1, qn plus 1 equals to qn bar, right? It flips. Whenever t equals to 1, it flips. But here if you see, clock is not same in, the clock is not shorted. You are giving clock only here, then this output is going as clock here, and then this output is going as clock here. So let us see what will be the next state. So if I write q0, q1, q2, initially it is 0 0 0. So as soon as the next cycle will arrive, as soon as the cycle will arrive here, this is 1, so this will flip to 1. It was 1 earlier, it will flip to 0, so this will be 1. Now these are positive edge trigger flip-flops, right? So it is going from 1 to 0. So this is a negative edge, so it will not trigger. So it will remain 0. Same as here, it is 1 only. So there is no positive edge coming. So it will also stay as 0 only. So this will be the next state. So the transition will only take place. So what do you mean by positive edge? So if we have a clock like this, whenever a transition from 0 to 1 happens, it is a positive edge. So this are positive edges, and whenever these transitions happen, then only your flip-flop will be operational, right? Else it will be inactive, it won't change any state. So here only here the positive edge pulse was applied. Here it was going negative edge, so it won't change. Here it was remaining as positive only. That is why it did not change. So I hope this is clear.
Yes, sir.
So the next question is, a ripple counter with positive edge triggered flip is given below. The present state is 0 1 0. Then what is the next state? So it is the same circuit as before. So if you can try it out on your own, I'll also try with you. Present state is 0 1 0. You are applying a positive edge here. Please try to solve it if you can. We'll do it together. Are you able to solve this? Let's do it together then. So again, similar to previous question, we are applying a positive edge here, right? So we applied a positive edge to this flip-flop. As soon as it sees a positive edge, it will recognize it input. So t equals to 1, that means this q0 will flip, right? So it was 0, it will go to 1. And here q0 bar will be 1, it will go to 0. So it will go to 1, it was 1, it will go to 0. Now again, it is a downward transition, so nothing will take place here. So it was 1, it will remain 1. It was 0, it will remain 0. And since again there is no positive transition, it will also remain 0 as it is. And so your output will be 1, 1, 0. So let me repeat. Initially you had 0, 1, 0 stored, right? When you apply a positive edge of the clock, this T flip-flop will activate, and as input to T flip-flop is 1, this Q0 will flip from 0 to 1. And this Q0 bar, it was 1. Since it was 0, it was 1. It will flip to 0. Now, since it is a positive edge triggered flip-flop, it won't change its state at this negative edge. This is a negative edge, not a positive edge. So it will not change, and it was 1, it will remain as 1. Here again there is no positive edge now. Since it was 0, it will remain at 0. So this flip-flop will not change its state. It was 0, it will remain as 0. So the final states are 1, 1, 0. So C is the answer. Is it clear? Okay, I am assuming it is clear since you guys are not answering. Okay, so next question is The number of unused states in the counter shown in the following figure is. So, okay. So how many maximum number of states can a counter have? If it has 3 flip-flops, it can have 2 to the power 3 states, right? It is 8 states total. But due to this combinational circuit, it may not go through all these 8 states from 000 to 111. So we have to find which states are unused, which states it never visits.
The unused states are minus from that.
Sorry?
So the unused states that are minus from the total states. Normally that is 2 to the power 3, 8. And the combined unused states, you have to remove them. That is the answer.
Yeah, the total number of states that we have that this counter will go through minus 8 will 8 minus the total number of states whatever this counter will go through will give us the number of unused states. Is that what you were saying?
Yes, sir.
So 6 is actually 6 are the used states, not unused. Unused states will be 2. So let us see this. J0, K0, J1, K1, J2, K2. So J0 equals to K0 is 1 always. J1 is Q0 dot Q2 bar. K1 is Q0 and J2 is Q1 Q0, right? K2 is Q0. So let's start with Q0, Q1, Q2. Let us start with 0, 0, 0. So J0 and K0 is always 1. So whenever in this condition in JK flip-flop, Qn plus 1 equals to Qn bar, right? It will flip. So Q0 will keep on flipping on every cycle because it is always J0, K0 are always 1. So in every cycle this will flip. So next cycle it will be 1, then 0, then 1, 0, 1, 0, like this. It will keep on flipping since these are always 1, right? It is like a behaving like a T flip-flop. When we short J and K, it is becomes a T flip-flop, if you remember. Okay, for now we have to find Q1. For Q1 we have to see what is J1 and K1, right? So J1 we saw is Q0, Q2 bar. Q0 0, Q2 bar will be 1, so it will be remain 0 only. Sorry, J1 will be 0, K1 is Q0, that is also 0. On 0 0 it will retain its old state, and J equal to 0, K equal to 0, there won't be any change. And if you look at Q2 for J2 and K2 we need to see, right? J2 is 0, it is Q1 Q0, and K2 is also 0, so it will be 0. Okay, so let me write it properly. J0, K0, J1, K1, J2, K2. It was 1, 1, 0, 0, 0, 0. Let us keep this handy. Okay, so next state This we have seen already. This flips, so it's 1 1. So it is always 1 1. Okay. J1 K1 is Q0 Q2 bar. Q0 is 1, Q2 bar is 1. So J1 will now be 1. Right. K1 is Q0. Q0 is also 1. So J1 K1 is 1 1. So now this Q1 will flip. It will become 1. And J2 K2 is Q1 Q0. Q1 Q0 is 0. K2 is Q0 is 1. In 0 1 condition, it remains as 0. JK flip flop, right? If you remember JK, Qn plus 1, 0 0, Qn, 0 1, 0 1 0 1 1 1, Qn bar. This is the truth table of JK flip flop, right? Okay. So in the next state now this is has flipped as it's expected. It is 1 1. Now here what we have, J1 K1 is what? J1 is Q0 Q2 bar. Q0 is 1, Q2 is 0, so Q2 bar is 1. It is again 1. K1 is Q0 is 1. J2 is Q1 Q0. Q1 Q0 is, let us look at J1 K1 again. J1 is Q0 Q2 bar. Q0 is 0. Q2 is 0. Q2 bar will be 1. So 0 dot 1 is 0. And K1 is Q0, that is 0. J2 is Q1 Q0 bar. Sorry, Q1 Q0, that is also 0. K2 is Q0, it is 0. So it will have the same state. Now this has flipped. Again, J1 is Q0 Q2 bar, it is 1. This is 1. J2 is Q1 Q0, that is 1. So it will flip 0 1. Now J1 is 0, K1 is 0, J2 is 0, K2 is also 0. 0 1 will remain. Now J1 is 0, K1 is 1, J2 is 0, K2 is 1. So it will be 0 0. So now if you see, we started with 0 0 0, we are back at 0 0 0. So it will now keep on repeating. So we have how many states we have gone through? 1 2 3 4 5 6. Then again first one is repeating. Like, so we have gone through 6 states. So we could have total 2 to the power 3, that is 8 states. The 6 are used states. So unused, 8 minus used, that is 8 minus 6 is 2 states. And which are those 2 states?
Yes, sir.
So which are the 2 missing states here? We have 0 0 0, 0 0 1,
001.
0 1 0, 0 1 1 is missing, right? So 0 1 1 is one of the unused states. Then we have, we also don't have 1 0 0, 1 0 0. No, we have 1 0 0. So we have 1 0 0, we have 101 is we have, 110 is we have, 111 we do not have. So 111 is the, these two are the unused states, right? So answer is 2. Is this clear?
Yes, sir.
Okay. So the figure below displays a mod n counter. The value of n is, so again the thing is we have to like figure out these relations that we saw here, what is j, k and everything. Then we have to follow this procedure to figure out what all states are we going through before it starts to repeat, right? So mod is actually the number of states we go through. So 6 is mod here. Similarly, we have to find what is the mod here. But before that, we have to determine, we have to solve this circuit and find out what are the inputs G1, D1, D2, D3. So let us do that. So let me just try to make it a little simpler. This is Q3 bar and this is Q2 bar, Q3 bar, this is Q2, Q3 bar, this is Q1. So input here is Q1, Q2. Okay. So here we see D3 is Q1, Q2, and we see D2. The D2 input is coming from here, and here input is, it is Q3 bar, Q1, Q3 bar. So this branch is Q1, Q3 bar, and here we have Q3 bar, Q2 bar, Q3 bar, Q2 bar. So D2 is Q1, Q3 bar plus Q2 bar, Q3 bar. That is Q3 bar, Q1 plus Q2 bar. This is D2. Now what is D1? This this inputs are here. So D1 is Q1, Q3 bar plus, what is this? Q3 bar, Q2, right? Q3 bar, Q2. That is Q3 bar, Q1 plus Q2. D1. So now we know the inputs, and D flip flop is very easy. In D flip flop, Qn plus 1 is always equal to D. Next state is just simply passed on as the input. So let us solve this. We have Q1, Q2, Q1, Q2, Q3. Let's also write D1, D2, D3. So let us write these equations again. D1 equals to Q3 bar, Q1 plus Q2. D2 is equals to Q3 bar, Q1 plus Q2 bar, and D3 is equals to Q1, Q2. Okay, so we will start with 0, 0, 0. This is the initial state. Then for the next state, we first need to find the D's. this D1, D2, D3. So D1 is Q1, Q3 bar, Q1, Q2. Q3 bar is 1, Q1, Q2 is 0, so it will be 0. D2 is Q3 bar, Q1 plus Q2, it will be Q3 bar is 1, Q1 is 0, Q2 bar is 1, so this will be 1. D3 is Q1, Q2 plus 0. So next state will be same as Q1 plus 1 is D, right? So next state is this previous state, 0, 1, 0. Now we again see D1 is Q3 bar is 1, Q1 is 0, Q2 1, it will be 1, D2 is 0, D3 is 0, it will be 1, 0, 0. Now D1 is 1, D2 is 1, D3 is 0, 1, 1, 0. Now what will be D1? D1 is Q3 bar is 1, these two are 1 is 1, D2 is 1, D3 is 1, Q1, 1, 1. Okay, so next state Q3 bar, it will be 1, sorry, it will be 0, it will be 0, it will be 1, 0, 0, 1. Next state is 0, 0, 0, 0, 0, 0. Now again we are at 0, 0, 0, we started with 0, 0, 0. So number of states that we have traveled is 1, 2, 3, 4, 5, 6. Again we start from 1, 2, 3, right? So 6 states we have traveled through, so mod is 6. So the answer is 6. Do you understand this?
Yes, sir.
Okay. So questions are fairly easy. What you have to do is just figure out.
Sir, this type of question may arises in exam.
They might, I think this one was too lengthy, so it may not come. But something like this you can expect. Maybe
So the
they,
criteria should be same before
sorry,
for the passing of exam, the question level and the type of the question.
it
And
will be very similar to your assignments. So practice your assignments well. You may get some questions like where as it is from assignment also.
yes, sir.
So the paper will be very much doable, I believe. So don't worry about it. If you know your concepts, you can do it. So these are a few lengthy questions. So, but they do see your concepts well, right? You can see, yes, we have to solve the combinational logic here. Then you have to remember what is D flip-flop. Then you have to see this synchronous counter. So how we are traveling through states. So it tests your three uh, concepts. So it is lengthy, but yeah, very interesting question. Good for practice. Okay. So now let's see the next question. Consider the circuit shown below that the propagation delay of the NAND gate is 2 nanoseconds and that of the counter is approximately 0. If the applied clock frequency is 1 gigahertz, the modulus of the counter is, okay. So first of all, what is this reset? So this reset, So whenever you will get 1 at reset, it will change all the state, all the outputs to 000, right? Sorry, it is reset bar. Whenever you get so you see it is bar means active low. So whenever you get a 0 at this reset, it will change all the outputs Q0, Q1, Q2, irrespective of their states to 000, whatever be the previous state. So that is what this reset will do. Now let's see what how to do this. Okay. So first of all, we are given the delay of the NAND gate is 2 nanoseconds, right? So this NAND gate is 2 nanosecond propagation delay. That means whenever you give some input here, let's say 111 input you gave here, after 2 nanoseconds it will reflect its change to the output, right? And another thing is the frequency, clock frequency is 1 gigahertz. So this is the clock frequency, the input frequency. So clock frequency means how fast the 001, 010. So this is a counter, right? 3-bit counter. It will count like this. So the how fast these states will change with 1 gigahertz frequency. And 1 gigahertz means 1 upon how much in time. So tau count is 1 upon 1 into 10 to the power 9, that is 1 nanosecond. Right? So between each, this clock is 1 nanosecond cycle. Right. So you say that uh, whenever an input will come to this NAND gate, before it will reflect any change at the output, 2 cycles of clock will already pass, right? Because this frequency is 1 nanosecond. So we will have, it will, let's say some change happened here, but 2 cycles will pass, then it will show its change. Do you understand this? Should I repeat? Okay, I'll repeat. So what I was saying is, we have been given the clock frequency is 1 gigahertz, right? 1 gigahertz means the delay is, sorry, 1 nanosecond, right? So between each count of the clock, there is 1 nanosecond delay. The delay of the NAND gate is 2 nanosecond, right? So whenever you give an input, after 2 nanoseconds, it will reflect some change at its output, right? So let us say at this moment, when you have 000 as a count, NAND gate changes. NAND, you activate the NAND gate. So it will take 2 nanoseconds. So by 2 nanoseconds means 2 cycles of this counter will pass. Then only some change we will see that is reflected to the NAND gate. Okay, so let us solve it. It will be more clear. So Q0, Q, sorry, Q1, Q2, Q1, Q0. So let's see time. At time 0, we have 000, time 1 nanosecond. We have 001, 2 nanosecond, we have 1010. Okay. So now at time equal to 2 nanosecond, we have 010. If you look closely, we have bubbles here, right? So, so it is like the actual input here after this bubble is 1, 1, 1. So when you give to NAND gate, if inputs are 1, 1, 1, the output will be 0. Sorry, it will be, yeah, 0. So it will give 0 here, but only after 2 nanoseconds, right? So this state, this 0, 1, 0 state will trigger NAND gate, but it will give this 0 only after 2 nanoseconds, right? So 3 nanosecond, 4 nanosecond will pass, then it will give 0, 0, 0. Since NAND will give 0, this reset will make everything as 0, 0, 0. So we will get 0, 0, 0 then. So in this, between these 2 nanoseconds, so wait, 2 more states will come, right? And this is 0, 1, 0, 0, 1, 1, 1, 0, 0. Then it will go to 0, 0, 0 again due to the delay of this NAND gate. If there was no delay, just after this 0, 1, 0, it would have gone to 0, 0, 0 at the next clock cycle. But since due to this inherent delay of the NAND gate, it will wait for 2 nanoseconds, and at the next clock, then it will make everything 0, 0, 0. So the mod of this counter is how many states we have wasted? 1, 2, 3, 4, 5. So mod is 5. Is this clear?
Yes, sir.
Okay. So next question is how many flip-flops are required to make a mod 129 counter? So try to solve it. Mod is 2 to the power, mod is actually less than or equal to the power number of flip-flops. So use this to determine how many number of flip-flops you need. 129 is less than equal to the power how many flip-flops. So you see to do our 7 is 128. So if I can 7 flip-flops make this, so 128 is less than equal to 128. Sorry, 129 is less than equal to, that is not true. So that means we need 8 flip-flops. 2 to the power 8 is 256. So 129 is less than or equal to 256. So we need 8 flip-flops. Right, if we have used 7 flip-flops, then we could only count to 128 states. We will miss one state. We, but we need to count 129 states. That is why we need an additional flip-flop. Is it clear?
Yes, sir.
Okay. So next question is same as previous one. So please look at it. Let me know the answer. Right. So here we need 47 479 is our mod. It should be less than equal to 2 to the power number of flip-flops. We saw previously 2 to the power 8 is 256. 2 to the power 9 is 512. So 479 is less than equal to 512. That is why number of flip-flop is 51. Sorry, 9. So this was easy. So let us see what we have next. Consider the following figure. Suppose you are asked to make a decoding circuit such that output y1, output y equal to 1 when counter is at state 2, 3, 4 and 5. Using a single gate, which of the following can be used to implement the given logic operation? Okay, so we have to build some logic such uh, so the inputs are A, B and C and output is Y. We have to give some gate here, right? Okay, so let me call it J0, K0, J1, K1, J2, K, or JK, JB, KB, JC, KC, J equals to K equals to all are 1, all J and K equal to 1. So that means at every clock cycle it will flip, right? But clock is A here, B here. So another thing to see here, there's a negative edge triggered, right? See a round here, right? So this is important to see. So this round means, this bubble means negative edge triggered. That means whenever the clock input will go from 1 to 0, then only transition happens. Okay, so let us see. So this C, B, A. Let us consider it as MSB, and this as LSB. So if we start with 0, 0, 0, we know A will flip always, right? Because clock is here. So at the negative edge, it will flip. So A will flip to 1, then 0, then 1. This will keep on continuing, right? 0, 1, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now whenever A A will go from A goes from 1 to 0, 1 to 0, then B will flip, right? Then only B will, this clock will be active and B will flip. So those transitions are 1 to 0, right? This, this, this. 0 to 1 it will remain 0, 1 to 0 it will flip. 0 to 1 it will remain 1, 1 to 0 it will flip. 0, 1, 0 to flip, right? And similarly here, whenever B will go from 1 to 0, this C will flip. So when B will go from 1 to 0, here it goes from 1 to 0, and okay, only once it goes from 1 to 0. So this will remain 0, 0, 0 till here. Now here it will flip 1, 1, 1, 1. So these are all the states that we will cover. Now output Y, we have an output Y with us, right? And Y at state 2, 3, 4 and 5, Y is 1. So at states 2, 3, 4 and 5, Y is 1. So it is 0, 0, 1, 1, 1, 1, 0, 0. Okay. So to find an expression for Y in terms of CBA, we can make a K-map, right? So let us make a K-map. CBA 0, 1, 3, 2, 4, 5, 6, 6. Right. So at 2 we have a 1, 3 we have a 1, at 4 and 5 we have 1, right? So this is C bar, C, B bar, A bar, B bar, A, B, A, B, A bar. So this will give us two pairs simply. So this is Y equal to C bar A, so C bar B plus C B bar. So that means Y equal to B XOR C, right? So this is what was asked. So to implement this Y equal to 1 when counter is at state 2, 3, 4 and 5. So to implement this, we need Y equal to B XOR C, and the question is which gate is needed? Single gate, so that is XOR. So this is the answer. Is it clear?
Repeat it, sir.
Okay. So now let us see the next question. The question is, what is the mod of the below counter? So again, like previous questions, so just try it once. So what we have to do, so we just have to find the inputs to these J and K, JC, KC, oh, sorry, it's not C, it is A0, A1, A2, A3, it is J1, K, J0, K0, J1, K1, J2, K2, J3, K3. Okay, so first step is to find all these J0, K0, J1, K1, J2, K2, J3, K3. Then we will propagate the states as we did earlier. So J0, K0 is, let us call it count enable, is E. Its input is E, enable, and E is always equals to 1 to run the circuit. So J0, K0 is 1, 1. J1, K1 is, J1, K1 is E dot A0, and E is always 1, so it is A0. Now J2, K2 is, so here we have A0. Now it is A1, so it is A0, A1, right? A0, A1, A0, A1. Here we have A0, A1. Now it is A2, so here it is A0, A1, A2. Okay, so now let us make the table. A3, A3, A2, A1, A0, here J0, K0, J1, K1, J2, K2, J3, K3. Start with 0, 0, 0, 0. So in the first cycle, J0, K0 is always 1, 1, right? It is always 1, 1. So this will always keep on flipping. A0 will flip. J1 K1 is A0, right? So it will be same as A0, it will be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Whenever it is 0, it will hold straight. When it is 1, it will flip. So now it's 1, it will flip. It will hold, flip, 0, 0, 1, 1, like this. A2 is A1, A0. So A1, 0, 0 is 0, 0, 1 is 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. So it will remain 0 until 1, 1. J2, K2 is 1, 1. It will flip. Then it will stay 1, 1, 1, 1. Then it will flip 0, 0, 0, 0. Then it flips 1, 1, 1, 1. J3, K3 is A3, A2, A1. A1, A0, A1, A2. So it is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Only here it is 1, 1. So it will remain 0 till here. And here it is 1, 1. Then it flips to 1. So if you see, it is a complete mod 16 counter. It has counted all 16 states. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Sorry, 15 only. Zeros there. So it counts from all from 0, 0, 0, 0 to 1, 1, 1, 1. Right? If you see this corresponds to 0, 1, 2, 3, 4, right? All the way till 1, 1, 1, 1, that is 15. So the mod of this counter is 60. Is it clear?
Yes, sir.
So again, as always in these questions, you just have to take care of a few things. First, find out what are the inputs. Then you see JK flip-flop. Then if you do not remember, write JK flip-flop table. Then 0, 0, it remains as previous state. 0, 1, it goes to 0, 1, 0, it goes to 1, 1, 1, it flips. This is the JK flip-flop total. Okay, so next question is, the clock frequency of 15 MHz is applied to a cascaded counter of modulus 3 counters, modulus 4 counters and modulus 5 counters. What is the lowest output frequency and overall modulus respectively? Okay, so give us some relations. Frequency is 15 MHz. It's 15 into 10 to the power 6 hertz. First information is this. Then we have mod 3, mod 4 and mod 5 counters. So we have mod, okay. So what is the overall mod? When they are cascaded, cascade means they're connected one after the other, right? We have mod 3, mod 4, mod 5. So in this the overall mod is the multiplication. M1 into M2 into M3 or any cascade number cascade. So here we have 3 into 4 into 5, that is 60 is the overall mod. So overall mod is 60 and the lowest output frequency is, so minimum frequency is given by input frequency divided by mod, overall mod, sorry. That is 50 into 10, 15 to the power 6 by 60. It is 450 to 50 kilohertz. So answer is 250 kilohertz and mod 60. Just remember this in cascade, and frequency is input frequency upon mod. These are always true. So these are formula based. Just remember this. Is it fine? Chat लगा लें. Okay. So let us see the next question. So it is same as previous. So please tell me the answer. We have now input frequency is 12 megahertz. F in is 12 megahertz. And mod R, we have mod 4, mod 5 and mod 6. So what is the overall mod and lowest output frequency? That means, right. So we have overall mod 4 into 5 into 6, which is 4 5 are 20, 26 are 120, and F min is 12 into 10 power 6 by 120, that is 100 kilohertz. So it is 100 and 120. Three cascade decade counters will divide the input frequency by. They will divide by their modules, like we know F min is F in by overall mod. So decade counter means 10. Yeah, 10. So overall mod is 10 into 10 into 10. The total is 1000. Fn will be Fn by 1000. It was easy. Okay, now this question. Please go through it once. Consider the following sequential circuit with X input and positive edge trigger D flip-flop. So positive edge trigger D flip-flop and determine the number of self-loop states. So self-loop and state transition diagram. Okay, so we have to make the state diagram for this, right? When as what is self-loop? In our state diagram, we have some state diagram like this. Self-loop is when it goes from one state to its own state, right? So how many these kind of loops do we have? That is the number of self-loop. So if we have one only, then self-loop is one. If two, it is two. If we have all, we have three. Right? These are self-loops. Okay. Okay. So here first it's the same procedure. D0 is X, D1 is Q0, Y is Q1. So let us start counting. Okay. So let's start with input Q1, Q0, X, then next step. So D1, D0, Qn plus, so Q1 plus, Q0 plus, the next it's and Y, and D0 is X, right? So this is X also. So if we start with some random, all the inputs 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, these are all the inputs. Now D1 we know is Q0. So D1 is Q0. So we will write copy all these Q0 values. It will be 0, 0, 1, 1, 0, 0, 1, 1. And D0 is X. So X is this column 0, 1, 0, 1, 0, 1, 0, 1. So these are D flip-flops, right? So Q n plus 1 is D. So Q0 plus will be D0, Q1 plus will be D1. So Q1 plus will be D1. So this whole row will copy here, and this whole row will copy here. So let us write 0, 0, 1, 1, 0, 0, 1, 1. Q0 plus is D0, 0, 1, 0, 1, 0, 1, 0, 1. What is Y? Y is Q1. That is same as this. This is Y. y is q1 right, not q1 plus. Okay, let us see what is y. Here we have q0. So as soon as clock will arrive, this q0 will become, so y is q1, right? We know that. As soon as the clock will arrive, this q0 will be q1. Q1 will become q1 plus is q0. So y is q0. So this is y 0 1 0 1 0 1 0 1. Okay, and let us make a state diagram. So how many states we have? 0 0 0 0 state, 0 1 0 1 1 0 1 0. I can put another one. 0 0 0 0 0 1 0 1 1 0 1 0 1 1 1 1. So we have four states, right? So we have four states. 0 0 0 1 1 0 1 1. Okay. Now when we will transition, so we can go from here to there. We'll go from 0 0 to 0 1 when input is x is 0 and okay. We'll go from 0 0 to 0 1. X is 1, y is 1. So we'll write here 1 1. We'll go from 0 1 to 1 0. X is 0, y is 0. 0 1 to 1 0. X is 0 and y is 0. 0 by 0. We write this x by y. Then we'll go from 1 0 to 1 1. X is 1, y is 1. 1 0 to 1 1. X is 1, y is 1. We go from 1 1 to 0 0. X is 0, y is 0. 0 0. Then we go from 0 0 to 0 1. X is 1, y is 1. This we have taken here. 0 1 to 1 0. We have taken 1 0 to 1 1. We have also taken. So what is remaining is this state also. So here if we get again 1 1, here if we again get 1 1, we will go back to this state. This state. So we have a 0 0 here. We'll go back to the state, right? X is 1, that means D0 is 1, Q0 is 1, Q1 is 1, Y0 is 1. So when we have X is 1 and Y is 1, we will go from 1 1 to 1 1. Similarly, in 0 0 to 0 0, X is 0, D0 is 0, that means Q0 is 0, D1 is 0, Q1 is 0, and Y is 0. So we will go from 0 0 to 0 0 back if we have X is 0 and Y is 0. So we have two self loops. One is this and one is this. So this was a tough question, but I hope you understand. So we have two self loops. Is it clear?
Yes, sir.
Okay. Next question is, a certain JK flip-flop has propagation delay of 40 nanoseconds. Largest modulus of the request counter. Okay. Operate at 8 megahertz. So tau PD is 40 nanoseconds. And tau PD is 40 nanoseconds and F is 8 megahertz. So if you remember the formula, F is equals to 1 upon 2 and tau PD that we saw last time also, where N is number of stages. Here stages means flip-flops. Let's call it N. Okay, so what will be N? N equals to 1 upon 2 F tau PD, 1 upon 2 into 8 megahertz, 8 into 10 to the power 6, 40 nanosecond, 40 into 10 to the power minus 9. So M is 100 by 32 is 3.125, right? Approximately 3.125. So these are, so number of flip-flops we are saying is 3.125. So that makes no sense anyways, but yeah. So n is less than equal to, we know, 2 to the power number of flip-flop, right? N is less than equal to, this is moderate, and write it as mod 2 to the power 3.125. So we know 2 to the power 3 is 8. So it will be more than 8, let's say 8 point something. So 8 is less than 8 point something, right? So maximum mod that we can count is 8. So question can be,
Okay, sir.
yeah, why
This
we
is
have taken this as 3 only, why not be 8? Why did not be rounded to 4? Because this is what we have obtained from the delay, right? So we can take some value less than this, but not more than this, right? You understand? If we have if result gives us we have 3.125 number of flip-flops, that means we definitely cannot have 4 flip-flops. We can have less than this. We can have 3 flip-flops. That will work. So if 3 flip-flop works, we can have 8 count. Okay. In the given figure, various states taken by the counter are, okay, VCZ means 1. So again, same thing we need to find. So this is LSB, this is LSB, JK, JBK, JCKC. First step is find inputs. J equals to K equals to 1. That means A will keep on flipping. JB equals to KB equals to A. JC equals to KC equals to A dot B bar. So for this, let us make table A, B, C, J, K, JB, KB, JC, KC. Let's copy it here. Okay. So as always, we start with 0, 0, 0. These are 1. So that means A will keep on flipping 1, 0, 1, 0, 1, 0, 1, 0. If you remember JK, QN plus 1 table, 0, 0 is QN, 0, 1 is 0, 1, 0 is 1, 1, 1 is QN bar. Here we have 1, 1, that is QN bar. That means it is keep on flipping. It is always 1, 1 because okay. JB is A. JB inferior A. So A is this. So it is 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. So when J is 0, 0, it will be previous state, and when it is 1, 1, it is QN bar. 0, 0 is previous state, 1, 1 is bar. So it will be previous state, 1, 1 is bar. 0, 0 is previous state, 1, 1 is opposite. 0, 0 previous state, 1, 1 opposite. 0, 0 previous state, 1, 1 opposite. C we have AB bar. AB bar, it is 0, 1, 0, 0, 0, 1, 0, 0, 0. 0, 0 means previous state, 1, 1 means flip, 0, 0 means previous state, previous state, previous state, flip. So these are all the states that it will travel. So it will go from 0, 0, 0, then 1, 0, 0. Okay, it is BCA, sorry. So these are written as BCBA, sorry. CBA, LSB, LSB. So I will have to write it again. rearrange it. Okay, so we start with 000, then 001, 110, 111. So if we see 000, 001, 110, 111, this one matches. This is the answer. Is it clear? Is this question clear? So we have done the same thing we were doing before. Find the inputs. Yeah, okay, thank you. So let us see the next question. We have to find the state sequence Q1, Q0. Okay. So this is what D0 is Q0 plus Q1 bar. It is an order, that is Q0 bar dot Q1 bar. De Morgan's theorem. Okay, so Q0, Q1, D0, D1, and D1 is Q0. So we start with 0, 0. D0 will be Q0, Q1 bar, that is 1. D1 will be Q0. Next state will be, we have D flip flop, Q1 plus 1 is D. So next state will be 1, 0. If we have 1, 0, then D1 will be Q0, that is 1. D0 will be Q0 bar, Q1 bar, that is 0. Next state is 0, 1. If we have 0, 1, D0 is again 0. D1 is Q0, that is 0. We have 0, 0. So we have 0, 0, D0 is 1, Q0 is 0. So okay, now we are repeating. Right. So we want to go further. Okay, so status, okay. Again it is Q1, Q0. Okay, and related Q0, Q1, so I'll just shift it. We have 0 0, then 0 1, then 1 0, then 0 0, 0 0, 0 1, 1 0, 0 0. So it will be this one, right? 0 0, 0 1, 1 0, 0 0, and again 0 1, 1 0, 0 0. Same as previous question, just easy. So the next question is the digital circuit shown is now divided by what counter? So by divide by, that is we are asking the mod, because we know f min is fn by mod, because mod is what is divided by. So we are asking the mod. So for that again we have to do the same thing. D0 is what? Q2 bar, Q1 bar, D1 is Q0, D2 is Q1. So again if we write Q2, Q1, Q0, put it aside, and D2, D1, D0, right? So we start with 0 0 0, D1 is Q0, D2 is Q0, D0 is Q2 Q1 bar, that is 1. Then we know Qn plus 1 equals to D for D flip flop. So these states will go here. We will have 1 0 0. So then again Q1 D1 is Q0, that is 0. Doing some mistake. So D2 is Q1, Q1 is 0, D1 is Q0, Q0 is 0, and D0 is Q2 Q1 bar, this is 1. So then we will have 0 0 1. Now again D2 is Q1, that is 0, D1 is Q0, that is 1, and D0 is Q2 Q1 bar. Q2 Q1 bar is 1. Here 0 1 1. Then D2 is Q1, D1 is Q0, D0 is Q2 Q1 bar. It's 0 1 1 0. D2 is Q0, so D2 is Q1, D1 is Q0, and D0 is Q2 Q1 bar. Q2 Q1 is 1 1, then Q2 Q1 bar 0 0. It's 1 0 0. D2 is Q0 for Q1, D2 is Q1, then it's 0. D1 is Q0, then it is 0, and D0 is Q2 Q1 bar, that is 0 bar 1, that is 0. That's 0 0 0 again. So now it will repeat. We started with 0 0 0. We are ending is again is 0 0 0. So this will repeat. So we have how many more? 1, 2, 3, 4, 5. Then it is again 1, 2, 3. Right? So you divide by 5 counter. Mod is 5. Okay. So I hope it is clear. Let us see the next question. The maximum clock frequency in megahertz of 4-stage ripple counter utilizing flip-flops with each flip-flop having a propagation delay of 20 nanoseconds. Okay, so we know f equals to 1 by 2 n tau pd, n is 4, tau pd is 20, f we have to find. So f is 1 upon 2 into 4 into 20 into 10 to the power minus 9. So it is so we have to in the previous question also it is n tau pd 2. It's n times tau pd. So it is 4 into 20 into 10 to the power minus 3. So it is 1 in megahertz, so it means 6 megahertz. So it is 1000 upon 80 is 12.5 megahertz is the answer.
Yes, sir.
Okay, so let us stop till here for today. You've done a lot of questions today. So if there are no doubts, let us close the session. If you face any difficulty, please feel free to email me or I'll upload the video right away. And if you have any doubts, you can comment on the YouTube video also. Yeah. Thank you everyone for joining.
Yes, sir. I will share if you have any doubt.
Okay.
Thank you, sir.